Okay, Team 4.
Alright, so we are Team 4. We're in charge of the feed, and this is our GR3 presentation about our chosen concept that we've gone with.
Okay, so our main problem is how are we going to transport the clay into the mixing? So we came up with an alternative from buying a backhoe. This solution is obviously going to be cheaper. So there's a few things that go along with this in our design ideas. Because we didn't want to move any earth, we didn't want to have to make any more additional foundation or any structures. So this solution of having a conveyor was the best idea. So we decided between either a belt or a auger or a screw conveyor. We decided to go with the screw conveyor for a couple of reasons. One is that there's less moving parts. Two, we have a member that has firsthand experience using a grain auger. And then also with this design, it's going to be easier to manufacture, put together, have replacement parts ordered or made in-house, and it's transportable. So how does it work? Well, auger conveyors are one of the oldest ways of moving bulk material, and it starts in the hopper here, which is going to be fed by using manual labor. So once the clay goes into the hopper, it drops down into the auger, and then it moves up to the spout here. And the auger is powered by a 5 horsepower motor, which is positioned at the top. And that position was chosen because all the benchmarks that we looked at all had the motor at the top there. So once the clay reaches the top, it then drops into the mixer. This is the interface with the mixer. So one of our design variables, obviously, is how high is the mixer. So we put that into consideration. And then also the length of the auger is another variable because we didn't want to exceed 45 degrees. So obviously, the more of an incline, the harder that your motor is going to work and less efficient your design is.
So, just looking at our auger frame, we took away the components, and we needed to figure out our diameter for these tubes that would support our assumed loads here. So for the clay weight, we went with 800 pounds, which is the volume of our auger completely filled. And then for the components themselves that will be mounted to this backbone piece, it was 723 pounds. And then, of course, our engine weight was 100 pounds. So we fixed these positions to the ground and then used a SolidWorks FEA study to see what would happen. And from the results, we got a bending stress of 13,000 psi, which is significantly lower than the yield strength of just a basic 1060 carbon steel. So we passed with a 2.5 inch diameter tube, but there could be two ways of making this design better, and putting a support from here up to here and then from here to here would get rid of this cantilevered position here. That could help. And then also a higher grade alloy would make this significantly stronger than the low grade 1060.
Alright, so to determine our motor choice, we need to know the type of auger and the auger RPM. So for the type of auger, since we're operating at the incline, you want to have a reduced pitch for the flighting. So typically for an inclined auger, you're using 1/2 to 1/3 pitch to prevent any material fallback. And so to determine the auger RPM, we found a really good website that had these trough loading types for material types. And for clay, lumpy clay, the loading type is 30% A. And that's basically, it's going to fill 30% of the trough, and it's the A, I believe, is the abrasive an abrasive tag. So using this table, looking at the material feed rate, which is about 140 cubic feet an hour, we determined that our RPM needs to be about 65 RPM. And the half pitch is considered when making that RPM selection. So from this table, we decided that a 9-inch diameter auger would be sufficient for the feed rate required. And of course, like Jacob said, since we're operating at an incline, we're going to have an efficiency. So at about 45 degrees, you have a factor of 2 for your incline factor, and that's taken into account into the total shaft horsepower for an auger at an inclination. So these are just a couple of factors. This is frictional horsepower. That's just how much horsepower is required to run it dry, and then this is how much is required to run it with the material in it. And then there's your inclination factor, motor efficiency factor, and then another little factor for the pitch. So total shaft horsepower required was about 3.5, so a 5 horsepower motor would be sufficient.
Okay, so we divided the entire conveyor system into individual components and did a failure mode and effective analysis, FMEA, on each individual component to kind of determine which component would be like most likely to break or fail. So this is an example of how we went about this. Here's the components, the function of each one, how it could fail, how that failure would affect the rest of it, and we assigned it numbers based on how bad the break would be for the entire design, how often it would happen, and how detectable it actually is. So right here I have listed the top 3 components that could fail based on multiplying each of these factors together to get an overall risk priority number. So the top one was the auger, which wasn't a surprise since without the auger, you cannot move the clay up. So if this fails, that would be a big issue. I know that you wanted to have somebody on site to weld and fix augers. So that would definitely be something good to have for both this conveyor system and the main auger in the clay machine. The next 2 were our end shaft and the shaft bearing. So if the shaft bearing fails, you can't really, the whole auger conveyor won't work anymore. The auger won't be able to rotate anymore. But luckily these aren't too terribly difficult to replace. And then this is the end shaft. This is located at the bottom of the auger conveyor system, and the reason why it ended up with such a high risk priority number is that you cannot detect if it's going to fail or not. And if it breaks in there, same concept with the bearing, the overall auger will no longer be able to rotate, and you would have to replace this part as well.
And we wanted to include the bill of materials in this presentation just to show you an estimate of how much this is going to cost. Obviously, it's not a cheap and easy fix, but it is a solution that's cheaper than buying a backhoe. And most of the parts you can purchase offline, or you can use that as reference in manufacturing in-house.
Anybody have any questions? All right, thank you.
One question.
Oh, yeah. Yeah.
Is your auger going to be one piece?
Yes.
Yeah. How long is it? The main
14 feet.
14 feet.
Yep.
Okay.
And that's based on, that is a variable, so if the mixer is lower than the auger.
We can always
But you,
change the
Yeah.
the intention is to make it one piece. Not
Yes.
Like, okay. Okay. Yeah,
Thank you.